All right, let's get started. If you didn't grab your homework, graded homework 1 and or 2 before class, make sure and grab it after class. It's just on this front table here. So any questions about the lab or the lumped capacitance method, anything else? Okay, so when we left off on Wednesday, we had introduced the lumped capacitance method. So that's the way we're going to deal with transient conduction. And kind of the big assumption of the lumped capacitance method is that you have basically no spatial temperature gradients. So you're saying that the thermal resistance of conduction inside an object is much smaller than the thermal resistance of convection and or radiation between the object and its surroundings. So basically, if the temperature comes to equilibrium really quickly within an object, and you can assume that it's the same or uniform at every point within the object. Okay, so we said that we can make this assumption if the conduction thermal resistance is much smaller than the convection or radiation thermal resistance. So we need to kind of be able to quantify that. So what does much smaller mean? So we'll talk about the validity of the lumped capacitance method for the first part of today. Okay, so we said if the thermal resistance of conduction, the ratio of the conduction thermal resistance to the convection thermal resistance is small, then the lumped capacitance method is valid. And this ratio is defined as, or named, I guess, the BO number, BI. We say this number is small if it's less than 0.1, 0.1. So assuming this condition is true, you can use the lumped capacitance method. So let's take kind of a visual look at what a material that had different BO numbers might look like. So let's take just a plain wall, just kind of a section of a plain wall. We're going to represent higher temperatures as increasing in the vertical direction. And then X from left to right. This wall is length L. And we have some heat transfer by conduction through the wall and then convection from the wall to the surrounding air. And then we're going to say the temperature, we're going to kind of draw this graphically. So we'll say we have some uniform flow down here that has a temperature T sub infinity and a convection coefficient H. So we're kind of plotting the ambient temperature right here with this dot. And then we'll say the surface temperature on the left-hand side, TS1, is quite a bit greater than the ambient temperature. So if you have a material that has a really small BO number, you're basically going to have a temperature profile that's almost flat within the material. So you have TS sub 2 over here, and this is for a BO number that's, say, less than or much, much less than 1. If you have a BO number that's on the order of 1, you're going to get something that looks kind of more like this. So TS sub 2, BO number is approximately equal to 1. You've got, you know, a decently significant difference between the surface temperatures on the left and right hand sides of the wall. So even for this case, using the lump capacitance method would not be a good assumption. So TS sub 2 is pretty different from TS sub 1. And then if you have a BO number that's much greater than 1, you're going to have a big decrease. Right, and the exact nature of these lines is going to depend on, you know, what's going on within the wall, but just kind of qualitatively. You'll have a big decrease in the temperature, and the lump capacitance method would definitely not be valid here. So basically you would have kind of, for this case, a small change in the temperature within the wall, and then kind of this really big change to get down to the ambient temperature. So really big temperature decrease. And then the same thing is true kind of for the rest of them. So, you know, a kind of medium amount of change within the surface, and then a medium amount of change between surface 2 and the ambient for a BO number on the order of 1, and then a large BO number, you have a big change within the surface, and then kind of a smaller change between, or within the object between surface 2 and surface 1. Yeah.
What's the B?
BIOT. I think it's named after a person. BIOT.
What's that again?
So that's this.
Oh, that's the definition. Okay.
Yep.
Okay, so just
The
make
BO
sure
number.
that-
Yeah.
Gotcha.
I assume it's maybe a French person because you don't say the T. Yeah. So this is the BO number. And that's just this ratio of the conduction to convection thermal resistances. Yeah. It does sound like you're saying BO, doesn't it?
Yeah, I thought you meant like B sub O, but I'm reading
Right.
BI, I'm like,
Yeah. Yeah.
Gotcha, thanks.
Okay. Cool. Okay, so if we want to write out how it's defined, or I guess how we can solve for it, for the BO number. Okay, so we said it's equal to conduction over convection thermal resistances, which we have expressions for, right? The conduction thermal resistance is L over Ka, and we're going to say L sub C here, and I'll talk about why we say L sub C in a minute. L sub C over Ka divided by 1 over Ha. So these are just the expressions for the thermal resistances that we already know. And if you reduce that, you get H L sub C over K. And this L sub C is a characteristic length. And we define it because we're not always going to be looking at just like plain walls that have a very obvious length. And so it's defined in order to be able to easily handle solids of complicated geometry. And it's just defined as the volume over the surface area. So last time, now that we have kind of this definition of the BO number as H L sub C over K, last time we were talking about this quantity H A sub ST over rho VC, rho times V times C. So this part we were saying was like the inverse of the thermal time constant, and it kind of determined how quickly a solid achieved thermal equilibrium with its surroundings. So we're going to rewrite it now in terms of a couple of different dimensionless parameters. So now that we have the characteristic length defined as the the volume over the surface area, we can express this as HT over rho C L sub c. And then do some more kind of algebra and rearranging. So now we've got h L sub c over k times k over rho times c times t over L sub c squared. So basically just rewriting this quantity on the left here. So this is the BO number, right? The first fraction. The second one, k over rho times c, we're going to define as alpha, which doesn't have a specific name. And then we're going to define basically this entire quantity. So let's rewrite that. The BO number times alpha t over L sub c squared. Now this entire quantity is going to be known as the Fourier number. This alpha t over L sub c squared is the Fourier number. So that's just kind of giving us another way to write this quantity here on the left. So h a sub s t over rho times v times c is now equal to just the BO number times the Fourier number. And this is an important quantity in our expression for the temperature as a function of time. So given that, we can now rewrite this theta over theta sub I, which remember is t minus t infinity over the initial time minus t infinity. So previously we had this equal to the exponential of like negative times this quantity. So we're just going to rewrite it as the exponential of negative the BO number times the Fourier number. Yeah.
Just to confirm, the only subscript c is on the L, every other c is specific to E prime?
Yes. Yep. Okay, any questions on this? This is kind of the culmination of what we're going to do for transient conduction. This is kind of the simplest model for transient conduction, and it's the only one that we're going to go over. There's a lot more complicated kind of transient or solutions to transient or canonical transient problems that you can come up with, but we don't really have time to get into them. So we're going to move on after this. So think about it for a little while. Let me know if you have questions. And this will be a key part of what we're doing in the lab next week. Okay, we're going to move on to convection after this. Going straight through. All right. Okay, so we talked about convection previously as like a boundary condition, right? And I gave an introduction, kind of what the physical mechanisms that cause convection are and how you can treat it, assuming you know this value h, the convection coefficient. And then in the first lab, we figured out how you can solve for h if you have experimental data as well. But kind of the main focus of the convection chapters, of which there are several, will be talking about kind of a more in-depth understanding of the physical mechanisms of convection, so talking about the boundary layers more, so getting into kind of fluids for a couple days, and then talking about how we can come up with empirical expressions for the convection correlation H. So you can solve convection problems if you aren't just given this convection correlation. Okay. So the first bit, we're mostly going to talk about kind of the mechanisms that underlie, the physical mechanisms that underlie convection. So we've said this before, you should know this by now, but convection is heat transfer between a surface and a moving fluid. And do you remember we talked about kind of the two different modes of heat transfer that, or the two different kind of mechanisms that combine to contribute to heat transfer by convection? So really close to the surface, you have primarily diffusion, so the random motion of the molecules is causing heat transfer. And then the bulk motion of the fluid further from the surface is kind of adding to that. So taking the heat that's transferred into the flow by diffusion and moving it. So do you all understand what I mean by like the bulk flow? Like the macroscopic motion of the fluid? Okay. And that is advection. So we'll just say here it's diffusion plus advection, and I trust that you know what that means.
Advection technically means like the movement of the mass, right?
Yeah. Yeah, so if you have like, and it's on like a kind of a macroscopic level. So we were talking about it if we have an open system, you have like energy transferred by advection from the flow in and out. So yeah, the flow has mass, and that mass has energy. Yep. And we also talked about how convection heat transfer rates depend on the nature of the boundary layers that develop near a surface. So convection depends on boundary layers. So I'll often write BL instead of boundary layer. So there are two types of boundary layers that are significant, and we also mentioned this when we introduced convection a couple weeks ago. The first is the velocity boundary layer, which we'll talk about first, and then the thermal boundary layer. So we'll draw a little cartoon boundary layer for the velocity. So let's say we have a flat plate, and this is the leading edge of the flat plate, so this is where it begins. And then upstream, you have some uniform flow that has a velocity u infinity. And then the y direction is also going to be important for talking about the boundary layer. So we'll define this as y equals 0, and then positive y in the upward direction. So the flow is uniform coming into the plate, and then when it hits the plate, the fluid particles right next to the plate are going to have the same velocity as the plate itself, which is 0, right? So you have a 0 velocity here, and you have a velocity, some finite u infinity velocity here. So you're going to develop this kind of profile where your velocity in the y direction is moving from 0 to u infinity. So up here we've got u infinity. Down here, u equals 0. And then this profile is a function of y. So the velocity as a function of y. And when you're close enough to the surface that the velocity of the flow is affected by the surface, is slowed down by the surface, you are inside the boundary layer. So down here is the velocity boundary layer. And then if you're far enough away from the surface that the fluid is not affected by the presence of the surface, you're in the free stream. And then kind of the important forces that are occurring in the boundary layer are, you all should have talked about this in fluids, but you have shear stresses that develop basically between the surface and the fluid next to it, and then between adjacent parallel layers of fluid. And those shear stresses develop because basically you have a 0 velocity here, a finite velocity here, and you have continuous fluid between those two velocities that's moving at different speeds next to each other. And the shear stresses are related to, so both the velocity gradient and also the viscosity. And we'll say tau sub s here. So that's kind of the surface shear stress. So we're talking about the shear stress right here at the surface, tau sub s right at the surface, and that's equal to the viscosity of the fluid times the velocity gradient in the y direction at y equals 0. So viscosity times the gradient of u du dy, so how the velocity is changing in the y direction at y equals 0, so at the surface. And this mu is dynamic viscosity. Oh, I'll just note that this is for Newtonian fluids. We won't consider non-Newtonian fluids, but just to have it stated. So for Newtonian fluids. And that just basically means that the viscosity is constant. Non-Newtonian fluids have variable viscosity. Okay, so we need some kind of quantitative way to say whether or not we're in the boundary layer. And we do that by defining a boundary layer thickness. So the boundary layer thickness, which we term, it's like small delta or del. So that's the y location where the velocity profile, the velocity in the boundary layer, has recovered to 99% of the free stream. So it's a location where u equals 0.99 u infinity. So you can say if y is less than del, fluid is in the boundary layer, and the effects of the velocity gradients and the shear stresses are going to be large. So fluid is in the boundary layer, and velocity gradients and shear stresses are large. Similarly, if y is greater than or equal to the thickness, fluid is in the free stream, and velocity gradients and shear stresses are negligible. And so we usually use the word like boundary layer, velocity profile, or just like velocity boundary layer to kind of describe how this u changes with y. Yes?
So when we assign this value to the boundary layer, are we more or less assuming it's like a fully developed flow? Because like in plate flow and fluids, we saw that like the boundary layer kind of continues developing
Yep.
along the plate.
Yeah. So yeah, the next thing that I was going to say is not only do you have kind of variations in the y direction because you have basically the boundary layer moving into the free stream, the boundary layer also develops in x. Yeah. So you can kind of draw this thickness, which starts at 0 at the leading edge and increases. So yeah, exactly. So basically you have like an entry region where the boundary layer is growing, and then you basically reach a point where it's fully developed and the thickness just kind of stays the same after that. So yeah, so this is kind of del as a function of x, thickness as a function of x. So if you want to know your fluid velocity close to the surface, you basically have to consider both dimensions, x and y. So you need to consider, okay, where am I along the x direction? Is my boundary layer still developing or is it fully developed? And then at that point, am I inside the boundary layer or outside the boundary layer? And if I'm inside it, kind of where am I inside it? So we can say velocity near the surface depends on x and y locations. So the main reason we care about, for fluids and heat transfer calculations, the main reason we care about the velocity boundary layer is because it is related to the shear stresses, which determine the friction coefficient. So if you remember from fluids, if you have flow moving over an object, you'll have some kind of skin drag, some friction related to that flow. And so the friction coefficient depends on the shear stress, which depends on the boundary layer. And that's defined as tau sub s over rho u infinity squared over 2. And then we should remember that C sub f and tau sub s are functions of x. So tau is related to the velocity gradient at the surface, which is determined by the nature of the boundary layer. That varies with x, so the shear stress varies with x. And because the friction coefficient depends on the shear stress, it varies with x as well. And again, these are all, so for the shear stress, you're interested in just the gradient at y = 0. So you don't really have to consider the y dimension for those parameters. Okay. Yep.
Conceptually, what is keeping the two denominator showing?
What is keeping what? Sorry?
That's it, since the denominator has been divided by 2, right?
Yes.
Is that kind of like showing a particular concept, writing it that way, as opposed to having it up top?
No.
Okay. That's just how it is.
Yeah. Yeah. I think, actually, it might be showing that this is kind of like kinetic energy, right? Because it's like
Oh,
velocity over 2.
Right.
So usually when you have dimensionless numbers, you say like, okay, this is showing that it's a ratio of these forces to these forces. So this is kind of writing like shear
Yeah.
to
1/2, yeah.
like inertial. Yeah. Good question. Yeah. Okay. So, all right, let's talk about the other important boundary layer, which is the thermal boundary layer. And there are a lot of analogs between the velocity and thermal boundary layers. So if you have flow over a flat isothermal plate and the temperature of the ambient fluid and the plate differ, then you will have heat transfer. So let's take, again, a flat plate. This time we're going to say the plate has some temperature, T sub S, the temperature of the ambient flow. And then we'll have, again, some uniform free stream that has temperature and velocity T infinity and U infinity. We have the same X and Y dimensions. So similar to with the velocity boundary layer, when the flow makes contact with the plate, right here at the leading edge, so x = 0, the particles right next to the plate basically come into thermal equilibrium with the plate. So the particles at the plate have a temperature of T sub S. And then the particles in the free stream have a temperature T infinity, which is lower than T sub S. So we'll just kind of draw this. So you can imagine here, this is like T = 0, and this is just showing that this is T sub S, and then up here is T infinity. So temperature is a scalar quantity, right? Not a vector, so we don't actually have like fluid flow. We're just representing the surface temperature here and just saying that, okay, the surface temperature is higher than the ambient temperature, and there's going to be some temperature gradient between the surface and the ambient flow. And then just like before, you're going to have kind of increasing temperature as you go down. And then this is the temperature as a function of y, this profile. And then again, if you're close enough to the surface such that the temperature is affected by the surface, you're within the thermal boundary layer. And if you're far enough away that the temperature is not impacted by the presence of the surface, you're in the free stream. And again, we have this same kind of definition of the boundary layer thickness. And just like the velocity boundary layer, it grows with x. So there's an entry region where the boundary layer is growing, and then you eventually reach kind of this fully developed region where it stays approximately the same thickness. And we call that del sub t. So the thickness of the thermal boundary layer del sub t is the value of y, or the y location, where, and just like before, we're going to write this in kind of a non-dimensional way. So where the T-surface minus the temperature in the boundary layer over T-surface minus T-infinity is equal to 0.99. So if the temperature in the boundary layer has recovered to T-infinity, then this would be T-infinity here, and you just get 1. So that's basically saying that the temperature has recovered to the free stream value. So we talked about how the velocity boundary layer is related to the friction coefficient, which is related to the force, the drag force on an object. We're going to show how the thermal boundary layer is related to the convection coefficient h. So if we wanted to write an expression for the conduction at the surface, so we're restricting ourselves to y equals 0, where the fluid velocity is strictly 0, right? So we can actually apply Fourier's law and come up with an expression for the conduction just at the surface. So the heat flux via conduction at the surface is K of the fluid. And again, it's okay to do this because the fluid velocity is 0. And then we're looking at the rate of change of the temperature in the y direction at y equals 0. So that's the conduction heat transfer. And then we can also write an expression for what the convection from the surface is. Just using our convection rate equation. And again, writing it in terms of fluxes because we're not talking about any specific distance. We're just talking about kind of per unit area, what the heat flux is. And then if we set these two equal to each other, we can solve for h, which is negative k sub f partial t partial y at y equals 0 divided by t sub s minus t infinity. So the nature of the boundary layer determines this temperature gradient, partial T, partial Y. So it determines how the temperature changes with the Y direction, and that directly impacts the convection coefficient. So it's kind of why we care about what's happening in the thermal boundary layer as it affects convection. Okay. Good? Everyone awake? You have like your Friday faces on. You're all like, okay. All right, 10 more minutes. Okay, so we talked about how the thickness of the boundary layer grows as you increase the x direction. And the surface temperature and the ambient temperature are fixed, right? Those are constants. So if we think about our partial T, partial Y, we've got the temperature difference fixed kind of over the entire boundary layer. And then our Y is growing, the Y direction. So as you move along the x direction, the temperature gradients are going to get smaller because you've got a constant on top and like an increasing value on the bottom. So temperature gradients, partial T, partial Y, decrease with increasing x. So the convection coefficient, H, which depends on partial T, partial Y, and Q, which depends on H, both also decrease with increasing x. So H and Q. Decrease with increasing x. Okay, so quick summary of all that. So you always have a velocity boundary layer if you have flow over a stationary surface. And the velocity boundary layer is related to the friction coefficient, which is related to the friction drag on an object. You'll have a thermal boundary layer if the ambient flow and the temperature of the surface are different, which is almost always the case. So for a given flow over a flat plate, you're going to have both velocity and thermal boundary layers that are developing simultaneously, but they do not necessarily develop at the same rate. And for any given x location, it's not guaranteed that the thickness of the velocity and thermal boundary layers will be the same. In fact, they probably always won't be the same. Okay. So we can say del and del sub t at a given x are not equal. And we showed that the thermal boundary layer was directly influenced the convection coefficient H. So we kind of just showed that one of the implicit assumptions that we've been making for up to this point is actually not really true. So when we've been doing convection calculations, you've just been given an H value, right? And you're just assuming that that H value applies to the entire surface, that it's kind of uniform over the entire surface, which we've stated as an assumption a couple times. You know, assume that H is uniform, like over the length of a fin or whatever. But we actually kind of just showed that the velocity gradient and therefore H does vary with the position along the surface. So we're going to be more specific about this and talk about local and average values of H. and therefore local and average values of Q.
Are we gonna talk about, or did we talk about calculating the thickness of the boundary layer? We just talked about rules based on the thickness. Is it just something that's given? Or?
Yeah, so when we get into more specific configurations, we'll talk about coming up with kind of expressions for determining what the boundary layer is and like the boundary layer profile and all that, yeah.
Okay.
Yeah, so this is just kind of conceptual introduction, and then we'll talk more about like specific flow over flat plate, horizontal plate, cylinder, sphere, internal flow, all that.
Okay. All right. Thank you.
Okay, so flow over an arbitrary object. So we'll just say flow over an object. It's kind of arbitrary shape. It's some temperature and velocity, T infinity, U infinity. And it has a surface area, A sub S, and a surface temperature, T sub S. And it's losing heat by convection or radiation. So as we said, H and Q, let's say this is convection. So H and Q vary along the surface. So if we want to know the total heat transfer rate, instead of just multiplying the flux times the total area, we have to integrate it. Because now the flux varies along the surface. So integration is kind of like a multiplication, right? So we're just taking the flux, integrating it over the entire surface, and that gives us the total heat rate, the total rate of heat transfer for that whole surface. And we can rewrite this using the convection rate equation, because really all that's varying over the surface is H. We're assuming that T sub S and T infinity are constant. So if we want to define an average H over the entire surface, then we can say, okay, the heat transfer rate is equal to this average H, and plug that into the convection rate equation. So H over bar. So really when we've been using H in problems previously, we've been using this kind of just assuming that either it's uniform over the surface or we're using this average convection coefficient. And the average H would then have to be defined as just writing the average in terms of an integral. So basically summing H up over the entire surface and then dividing by the surface area. So it's just an average written in integral form because H is varying with A. You're all like, circular integrals, oh god. Okay, so over a flat plate, we know that H just varies with X, right? So for flow over a flat plate, this is a little simpler. And we can just kind of integrate H over the length in the X direction that we're considering, and then divide by that length. So calculating Q always depends on knowing H, the convection coefficient, And we showed that that depends on the boundary layer, right? So that's determined by the fluid properties, surface geometry, and flow conditions. So, kind of our culminating statement, we can say determining H is often called the problem of convection. And that's what a lot of the rest of the convection chapters are going to be devoted to, determining H for different physical situations. Okay, 2 announcements. If you haven't signed up for a lab time, please do so. The labs are starting next week on Tuesday. And I will post a handout either today or over the weekend, depending on how the data collection goes for us. And then try to give it a read through before recitation or at least before your lab. I think it'll really help kind of understanding what Abby is talking about and what they're talking about during the data collection. Okay, thanks.